Welcome to Xiaol.x, where visual intelligence meets immersive storytelling. In this episode, we explore Monet, reasoning in latent visual space beyond images and language. Let's dive in.
We can rotate objects in our mind without uttering a single word. Your brain effortlessly simulates that turn. But for state-of-the-art AI, this simple act is often a brick wall. The reason? Discrete words. Labels like cat or dog only point to a single snapshot. They miss the seamless, high-dimensional space our thoughts move through. Style, context.
Why does artificial intelligence trip over the visual intuition humans take for granted? We instantly know a ball will settle inside a cup or that this shape can't exist in the real world. But AI systems are built on statistical pattern matching, not on a lifetime of embodied common sense. Without that grounding, even
the old way of building perception systems leaned on external tools, bolting on coordinate predictors like a pair of glasses. They could tell you where something was, but not what it meant. These rigid setups lacked internal flexibility, produced brittle outcomes, and often choked on latency. Giving an AI a pair of glasses.
Previous models relied on slow, rigid external tools to inspect tiny details. Each frame captured one line at a time, taking seconds to form a grainy image. The new integrated vision engine changes that. A built-in adaptive camera captures the entire field in 1/10 of a second. Crisp, colorful.
Imagine an AI that doesn't describe a picture in words, it actually thinks with it. Monet replaces bulky external tools and discrete text prompts with a smooth internal stream of visual thoughts, continuous latent embeddings living inside the core model. The result? Human, like integrated reasoning.
Until now, generative models waited for us to type instructions. Monet does something radical. Instead of words, it forms internal visual thoughts, dense, fluid embeddings full of shape, color, and mood. Those thoughts map directly to images, skipping the...
How do you grade a thought that has no words and infinite possibilities? VLPO, Visual-latent Policy Optimization, treats a model's latent imagination as a probability distribution. Mean and uncertainty become measurable, optimizable. By sampling from this distribution, the
sorts. Imagine if ideas could be modeled not as fixed points, but as flowing probabilities. The VLPO algorithm makes it real. By treating thoughts as distributions, it learns to sample, reshape, and refine them, just like training a neural network, without locking us into a single state.
Let's zoom in on how Monet 7b handles latent reasoning. During inference, the model automatically emits a special start token, enters a fixed-length latent space, and reasons before returning to natural language. These orange squares are the latent embeddings, compact, learnable workspaces that allow the model to solve.
Memorizing a shape is easy. Understanding the logic behind how it moves, that's intelligence. From a single two-dimensional view, the model infers hidden angles, builds a 3D representation, and locks it into a stable form. No text description, no memorized template, just geometric reasoning. And when
in our mental rotation demo, Monet compares two chairs and decides if they're the same model at different angles. The target chair stays put, the other is turned to a random orientation. She imagines rotating it internally. In less than a second, her mental image locks in. Within 5
To really understand new puzzles, a model needs more than memory. Memorization simply matches what it's seen before. Great when the puzzle is identical, but it crumbles on anything new. Generalization, on the other hand, extracts abstract visual rules. Top left is always red, center is blue, the sequence rotates. With those rules in
This is Monet, our model that discovers abstract reflection rules directly from data. It studies how numbers relate across a hidden mirror plane, then learns to enforce that symmetry. On the left, raw samples. On the right, Monet's corrected reflections.
Teaching a computer to have an imagination comes with a hefty price tag. Today, most AI just sees images. It matches patterns the way a lock scans a key. Humans, by contrast, think with images, rotating, visualizing, and reasoning in real time, using a fraction of the energy.
Watch what happens when we mentally zoom into a single bar on this nitrogen chart. First, we highlight pond 3. Now, instead of reading a tiny label, we fly inside the data itself. Each value becomes a landscape, and the top surface reveals the exact measurement.
We're witnessing the transition from AI that simply uses tools to AI that begins to possess intuition. Today's systems are largely data-driven, powerful but narrow. The leap in the middle, enhanced pattern recognition and abstract reasoning, is a major step toward true visual intuition.
Training state-of-the-art AI models is powerful, but not magic. Here's the full pipeline. It starts with vast datasets, moves through careful model design and weeks of training on hundreds of GPUs, and only then reaches deployment. The upside? Stunning accuracy and generalization. The trade-off is a highly complex and expensive training pipeline.
Every time a model pauses to call an external tool, it hits a wall of latency and computational cost. Compilation, execution, data transfer, each step adds friction. And when we ask it to think by generating code, the path is brittle and slow.
Everywhere we look, the future is arriving. Robots learning beside us, sunlight powering entire cities, rockets that return to fly again. We are decoding life, bending the rules of computation, and rethinking how we move, build, and connect. Together, we are designing.
Have you ever wondered why analyzing a detailed image or a complex chart sometimes feels incredibly intuitive to us? You know, that instant recognition of a pattern or a spatial relationship. But it's notoriously hard for even the most advanced AI models.
It's the ultimate cognitive bottleneck, really. We can, mentally rotate a 3D object or visualize a transformation without ever needing to describe that process out loud.
Exactly.
That internal, non-linguistic visual workbench. That's what AI has just struggled to replicate. MLLMs or multimodal large language models, they can see an image, but they can't truly think with it.
Exactly. And that failure point, that rigidity in visual reasoning, is the subject of the deep dive we're taking today.
All right, let's get into it.
Our mission is to unpack a paper titled Monet, Reasoning in Latent Visual Space Beyond Images and Language. We're going to analyze the core problem of this visual rigidity, the really ingenious solution the researchers designed, and the results they got.
Okay, so let's set the stage. The old way. For a while now, researchers have been chasing this idea of MLLMs using auxiliary visual evidence during their reasoning process.
Thinking with images idea.
Exactly, often called chain of thought or CoT. This was sort of the first attempt.
And the initial way they did that was, well, it relied really heavily on external tools. Think of it like this. If the MLLM needed to focus on a detail, it couldn't just think about zooming in. It had to explicitly generate a command.
It had to predict key region coordinates and then send that command to a totally separate visual tool to create a cropped secondary image.
More, if the task was even more complex, like calculating depth or drawing a bounding box.
Then it had to invoke external tools entirely. Sometimes it even had to generate executable code for those tools to run. Just a whole other step.
And this whole architecture, it had two fundamental limits. This is why the old way was such a problem. First, it was just rigid. It had terrible generalization.
Right.
If you train a model primarily to predict coordinates for a bounding box, it gets incredibly good at that one thing.
And completely fails when you ask it to do something more abstract, like visual subtraction or spatial rotation.
The tool is just wrong for the job, and the model has zero internal flexibility to adapt.
It's the difference between using a specialized calculator for one equation versus, possessing the general skill of mental math. The model becomes task-specific, not actually intelligent.
You can't just generalize from a bounding box tool to figuring out how a shadow would fall in a new environment. It doesn't work.
No.
Which brings us to the second big limitation. The latency and what they call the cognitive burden.
Yeah, because that tool-dependent reasoning required asynchronous multi-turn inference. So you send a request, you wait for the visual tool to return the result, then you process it.
It adds all this latency, making deployment incredibly slow.
And it slows down training, too. During the training phase, models would just fail to generate valid tool calls or code all the time.
So the trainers had to spend huge amounts of time dealing with garbage outputs.
Right. It just increased the overall training difficulty dramatically. The model was spending way too much of its energy just managing the tool chain instead of, solving the actual visual problem.
So, okay, if relying on external tools was rigid, slow, and a computational headache, how do you pivot to something that feels more like human abstraction?
Yeah.
They're intuitive.
Well, here's where Monet steps in, and it gets really, really interesting.
Okay.
Monet proposes a fundamental shift. Instead of generating a language command for an external tool, the MLLM learns to reason directly in the continuous latent visual space.
Okay, what does that mean, latent visual space?
It means it generates an internal, non-linguistic representation, an intermediate visual thought, if you will, that represents the action needed, like a zoom or a rotation.
So the model isn't saying, in text, I need to crop this section at coordinates x, y.
Exactly. It internally spits out a specific sequence of special tokens, this latent token segment, which represents the numeric visual coordinates themselves, or maybe the transformation matrix, but as a continuous embedding.
It's a thought, not a verbal description of a thought.
Precisely. This is pure internal computation. Think of these latent embeddings as just high-dimensional continuous vectors. They capture complex, nuanced information far beyond what a discrete text token like the word crop ever could.
So these vectors are the model's internal concept of the visual manipulation it needs to do.
You got it.
That sounds powerful, but generating and using these continuous embeddings, that must be a massive technical headache, right? If the embeddings are continuous, doesn't that make the search space, like, infinite?
That's exactly why previous attempts at this failed. They identified two core hurdles: the high computational cost of aligning these complex embeddings with thousands of image tokens, and just not enough supervision over the latent embeddings themselves.
You have to teach the model how to think visually, and how do you supervise a thought?
Right, so they developed this very carefully structured multi-stage pipeline. It all started with an intensive supervised fine-tuning stage, or SFT.
And first, they needed really high-quality data.
Yes, they curated the Monet SFT 125K dataset. It features 125,000 of these chain of thoughts across complex geometry, charts, OCR, real-world problems.
And the quality here was key, wasn't it? They didn't just grab any old data set.
No, they used a really clever filtering technique. They only included the hard problem samples that the base model failed to solve without those intermediate visual steps.
Ah, so that ensures the latent reasoning is actually necessary and accurate for solving the complex tasks.
Exactly. It stops the model from just generating unnecessary internal thoughts for easy problems.
Okay, so they have the data, they put it through this three-stage SFT pipeline. But you mentioned the real breakthrough came with reinforcement learning, or RL.
This is where we run into that continuous versus discrete problem again. Standard RL methods for LLMs, like an algorithm called GRPO, are designed entirely around optimizing discrete text tokens.
A word in a dictionary. A finite choice.
A finite choice, yes. And continuous latent embeddings are infinite. It's not a word. It's a point floating in this high-dimensional space. How do you reward movement toward a good action in a space with infinite possibilities?
You can't, not directly.
If you try to use GRPO, it would only optimize the text parts of the model, the question and the answer, and it would leave the core visual reasoning component, the latent embeddings, completely untrained during that crucial RL phase.
So this raises a huge question. How do you reward a thought that isn't language, especially when that thought is continuous?
Their answer was VLPO, Visual-latent Policy Optimization, a novel RL algorithm tailored for this exact challenge.
Okay, so what does it do differently?
Instead of treating the latent embedding as an infinitely precise fixed point in space, VLPO models it as a sample that's drawn from a Gaussian distribution.
Ah, so you're approximating the continuous output. You're basically giving it a probability curve.
Precisely. By modeling it as an estimated probability distribution, they could then estimate the output probability of these continuous latent embeddings.
Which is the technical trick that lets them compute the policy gradient updates.
And that means the external reward signal, getting the final answer correct, can finally flow back and directly optimize the quality of those internal latent visual actions.
That's the game changer. The VLPO pulls the policy's latent embeddings closer to the good action embeddings that led to a positive outcome. It's rewarding the model's internal imagination.
And it's incentivizing it to generate better visual concepts without needing any external tools. That direct optimization of the continuous latent space is what gives Monet its edge.
So after all that incredible technical complexity, what does this actually look like?
Well, the results are pretty impressive. Monet 7b, their final model, showed consistent and pretty significant gains. It improved the base model by between, say, 4.25% and almost 10% across various benchmarks.
But the real breakthroughs, the cognitive leaps, you see them in the specific demos they provided.
Let's dive into those visual examples because they're great. The first one is a demo of its capacity for 3D spatial reasoning.
Okay.
The task was to look at two chairs arranged at a specific angle on a floor, and then pick the image that correctly matched that precise angle from a set of 4 options.
A traditional MLM would really struggle with that. It might have to try and verbally describe the angle or calculate coordinates. What did Monet do?
It bypassed the verbal bottleneck completely. The model's output literally said it would focus on the visual representation of the chairs. Latent embeddings latent.
Wow.
It generated an internal visual thought representing that focused angle, processed the spatial relationship purely in the latent space, and only then did it output the final answer.
It used visual imagination instead of an external geometry tool. That's a huge deal.
It is.
Okay, let's look at the second demo. 2D transformation. This is where it gets to abstract rule recognition.
Right. So the model was shown the number 4, and then it was shown that the 4 had been reflected twice. First horizontally, then vertically.
Okay, a complex transformation.
And the task was to apply that exact same sequence of abstract transformations, horizontal flip, then vertical flip to the number 5, and then pick the resulting image.
And this requires understanding the abstract rule of transformation, not just recognizing a flipped image. Is it just memorizing flips from its training set?
That's the critical question, and the latent reasoning proves it isn't memorization. Monet 7b successfully identified the complex transformation pattern on the 4, generated a latent embedding representing that rule, and then internally applied that rule to its concept of the number 5.
And it got the right answer.
It got the right answer. And its success on these unseen puzzles shows it generalized the visual rule in latent space.
That is really robust. Okay, and the third demo, this one shows how it handles really complex diagram reasoning, which is vital for interpreting documents and charts.
Yeah, this demo showed a kind of hierarchical reasoning. So you have a dense, detailed bar chart, and the question is, which country is the top sales country and what is the exact amount?
So it needs to do two things. Find the right section and then read the precise number. Zoom and read.
Exactly, but internally. Monet 7b initiated its latent thinking mode. It generated an internal visual thought, an embedding that acted like an attention mechanism to zoom in or highlight the specific section labeled top sales countries.
So it's focusing its internal visual attention without needing to render a new cropped image.
Yes. And after generating that latent focus, it then had the clarity to extract the fine-grained data like United States sales at 1,241.60 M and deliver the correct final answer.
That ability to both abstractly focus and extract detail is huge for document analysis.
For sure. And this capability directly translated to better generalization. Monet achieved the best performance on the really challenging visual puzzles benchmark.
And that's all abstract visual logic puzzles it hasn't seen during training.
Correct. Which confirms that VLPO is the key here. It incentivizes that truly useful, abstract, latent reasoning that can transfer to new out-of-distribution problems.
That generalization edge really does suggest the model is learning an internal language of visual manipulation, not just how to use tools better. But even this breakthrough method has a catch, right? It can't be that simple.
You're right. The primary limitation is the initial investment and complexity. Monet relies on that complex, multi-stage SFT pipeline we talked about.
The distillation steps, the specialized data curation.
All of it. All significantly increases the overall training complexity and overhead compared to a simpler, single-stage fine-tuning. This is not a cheap upgrade.
And I also noticed the point about the reward design. While VLPO is powerful, the researchers admitted their current reward design is pretty simple. It just rewards accuracy and correct format.
That's right. They did not explicitly reward the latent reasoning behavior itself. In other words, they didn't incentivize the model to use the latent tokens more or to generate a specific type of visual thought.
Wait, if the model isn't being rewarded for how it thinks, but only for the final output, how do we know what it's actually thinking? Doesn't that make the reasoning kind of opaque?
It definitely increases the opacity, but their ablation studies give us some insight. We know the process is necessary because when they tried applying the older text-focused GRPO method, it provided minimal benefits.
So VLPO was the necessary piece of the puzzle.
It was. Future research will need to explore more complex behavior-shaping reward designs to see if they can, explicitly nudge the model toward more intuitive or human-readable forms of internal visual thought.
What really stands out to me is that Monet represents this crucial step, shifting MLLMs from relying on slow, rigid external tools to developing internal, continuous, abstract visual thoughts. It's moving AI closer to true visual intuition.
The foundation for a genuine, flexible visual imagination is being built right now.
AI, the first frontier.